Hi there, this is Aaron Miller. Today I'll be presenting on circuit protection. Alright, let's get right into it. So overview, what we're going to be talking about, we'll talk about the theory of electricity, we'll talk about volts, amps, and circuitry, then we'll move on to why we need protection, a little bit about surges, we'll talk about the types of circuit protection. We have fuses and circuit breakers, we'll discuss how they work, operating practices, important circuit breakers, and their location. And we'll also talk about load shedding here as well, and then after that we'll wrap it up with a conclusion and the sources for the presentation. So the theory of electricity, how does electricity work? If we want to have a solid understanding of circuit protection or circuit breakers, we first need to get clear on what a circuit is and why it might need to be protected. Simply put, a circuit is a route electrons flow through. It is the way electricity is transmitted. There are three basic components of an electrical circuit. First, we have the source of power. A battery, for example, could be the source of power. Then we have the component that is using the power supply, like a light. And then finally, we have the conductive wires which connect the two. So two terms which are commonly used when talking about electricity are volts and amps. A volt is a measurement of how much force that source of power is pushing electric current with, and amps are a measurement of the rate of electric flow through a circuit. So volts are more so pressure, amps are more so volume. Okay? Great way to think about this is to picture two bags full of water, right? If we put a 5-pound weight on one bag like we see in the left picture and a 25-pound weight on the other bag like we see in the right picture, and if we were to poke a hole in each of the bags with a pen, the pressure of the water flowing out of the one with the 25-pound weight would be much higher than the hole with the bag with the 5-pound weight on it, right? So if we poked holes in each of them, we have that heavier weight on the right-hand bag pushing down on it, and it's going to push that water out with more force, more pressure, think more volts, right? And you can see that by the little pieces of paper the gentleman has up above here. 120 volts versus 12 volts, right? More pressure, more power through it, more volts, okay? And then let's say while that water's flowing out, we were to grab a measuring cup, okay, and we put it under that stream of water coming out for 1 second, and the amount of water we were to grab in that 1 second, that would be the amount of amps, right? So depending on the amps or the volts of a circuit, there will be varying needs for the gauge of wire that is used. The more amps or the more volts, the bigger the wire needs to be in order to handle it without overheating. Okay. So why do we need protection? Well, it comes down to surges. So what is a surge? It's a random quick spike in voltage. Again, recall that voltage is a measurement of pressure. If we all of a sudden drastically increase the pressure in the circuit, we could do some real damage to the components in that circuit. So we need some sort of fail-safe that can act as a buffer against these random surges of voltage. So we have two types of circuit protection. We have fuses and circuit breakers. So a fuse is placed in relay, so between the power source or the battery and the component using the power source or the load, right? So between the battery and the load we have the fuse. So if there's a surge in the voltage coming through that circuit, it'll heat up a metal wire or strip inside the fuse until it melts. Once it melts or is blown, the circuit is completely offline and no power will go to the appliance until the blown fuse is replaced. And that's something that you really can't do in flight. For that reason, people don't really use fuses too much in modern aircraft. They've moved on to circuit breakers. So this is the more modern solution to circuit protection. The main difference between a circuit breaker and a fuse is that a circuit breaker is resettable in flight. Here's how it works. At a predetermined overload, the heat caused by current passing through the disc causes the disc to reverse its curvature or snap. The snapping action separates the electrical contacts and opens up the circuit, as we can see in these two pictures, right? So on the left we have a closed circuit breaker, so this is allowing the current to flow through, and over here we have a pop circuit breaker, right? This is not allowing the current to flow through. It's a short circuit, right? So that power is no longer flowing through to appliance or device that is on the other end of that circuit. Some operational considerations. So in 2009, the FAA came out with a special airworthiness information bulletin, and in it they outlined some suggestions with regard to circuit breaker operation. So essential circuit breakers should be reset in flight only once and after at least 1 minute if there is no remaining smoke or burning smell and the affected system and equipment is needed for the operational environment. So the FAA is saying, hey, this is the only time that we should reset a circuit breaker. That's all. The FAA also advises do not reset any non-essential circuit breakers in flight. So if you don't need it to safely execute that flight, don't reset it. Third one, revise the pre-flight checklist so to delete circuit breakers in, right? So when we're going through a pre-flight check and it tells us to check the circuit breakers, if there's a circuit breaker that's popped, don't reset that circuit breaker if there's a related maintenance malfunction. Okay, get a mechanic and have them look at it. There was actually an incident that happened where a crew reset the in-flight weather radar circuit breaker, and the crew prior to their flight, it had popped on them without them knowing it, and this crew reset it, and they believe it ended up leading to a fire because they reset that circuit breaker. So if you get in the plane and a circuit breaker's popped, investigate it a little bit. Don't just willy-nilly pop that thing back in. And last one here, never hold a circuit breaker that wants to pop. So never keep that thing pressed in. This will allow the surge to pass on to the wiring and appliance down circuit of the breaker, leading to damage and even potentially a fire. So a good question that comes up is, this could potentially come up on a check ride or stage check, can we pull a circuit breaker to deal with inoperative equipment? So the scenario is you get out to the airplane and something is inoperative, right? It's not required by 91205 or the TCDS or any of the supplemental type certificates or an AD. So we refer to FAR 91213, which states inoperative equipment can be dealt by deactivating and placarded inoperative. However, if the deactivation of the inoperative instrument or equipment involves maintenance, it must be accomplished in accordance with FAR Part 43 of this chapter, so a mechanic needs to do it. So, that begs the question, is pulling a circuit breaker on the ground to deactivate it part of preventative maintenance that we as private pilots are allowed to perform? And that is not the case. If you look in Part 43, pulling circuit breakers on the ground is not part of preventative maintenance. A private pilot cannot pull a circuit breaker on the ground to deactivate inoperative equipment. A mechanic would have to do it and make an entry in the maintenance log. Okay? Next, let's talk about some key circuit breakers that we're going to want to be aware of and have this in the forefront of our mind. We almost want to memorize the position of these circuit breakers because the timely location of these circuit breakers can really be a deal breaker in flight. If we're fumbling around trying to find a circuit breaker, we're wasting precious seconds, and you'll see why that's important here in a second. So if we look at the emergency procedures in the AFM for the Seminole, if we look at some of these procedures, the alternator failure. So if we have an alternator failure, it requires us to reset the alternator circuit breakers, which are located right over here. So what is that? Row 2, column 15 and 16. If we have an electric pitch trim runaway, right? Very, very dangerous. That calls for us to pull that circuit breaker, row 3, column 1. If our autopilot pre-flight test fails, we pull the autopilot circuit breaker as well as the pitch trim circuit breaker. If the pitot heat fails, we're supposed to reset that, and that is located in row 2, column 2. If the hydraulic gear pump fails, we're supposed to reset that, okay? Row 2, column 12. Another good one, and this will be the last one. If the engine starter won't disengage, which is extremely dangerous, right? Could surge the entire system and blow up a lot of stuff. If the engine starter won't disengage, we're supposed to pull that circuit breaker. So it's located right there, row 1, column 12. While we're on the circuit breaker schematic, let's talk about load shedding. So let's assume worst case scenario. We experience a dual alternator failure in IMC. we're now running entirely off of the emergency battery and the emergency battery bus. It'll power the emergency bus for 30 minutes. Then after that, we have the battery, which if fully charged can supply 13.6 amps for 1 hour. Should the situation call for it, we may need to think about load shedding or reducing the demand on the battery. So how do we load shed? We load shed by either pulling circuit breakers or turning equipment off, flipping the switch in the cockpit. And how do we know which ones we should turn off? Well, on the circuit breakers, and I wish it showed it in this schematic, but they don't, but on the circuit breakers there will be a number, and that number tells us how many amps that specific device is pulling. So it makes sense to start with the unnecessary and high amp circuits first. So to do that, simply pull out that circuit breaker and you've shorted out that circuit, no longer drawing energy from the battery. So, really effective and timely load shedding can save you precious minutes of battery power and allow you to safely end a flight. Alright, so in conclusion, a circuit is built to handle only so much voltage going through it. When a surge occurs, we need some sort of failsafe to prevent that surge from damaging the appliance or wiring in that circuit. In modern aircraft, circuit breakers are that solution. When the voltage is too great, the circuit breaker pops and shorts the circuit, preventing that surge from reaching the appliance. Some considerations with regard to operating circuit breakers as a pilot are: 1. Don't reset non-essential circuit breakers. If you need to reset a circuit breaker, only do it once and only after waiting at least 1 to 2 minutes for the internal components to cool down. Number 3, don't pull a circuit breaker as a means of disengaging inoperative equipment prior to a flight. A mechanic is needed for that. And number 4, next time you're in the Seminole, take a second and try to locate some of those circuit breakers I talked about, some of the key ones, some of the ones you might need in a pinch, like the electric trim circuit breaker and the starter circuit breaker. Thank you so much for taking a second and watching this. I hope you learned a little bit. I know that I learned a lot going through this. Here are some of my sources: the FARs, Understanding Electrical Systems by J. Mac McClellan, Flying Magazine article, fantastic, highly recommend you go read that. Piper Seminole AFM, and then Aircraft Systems by David Lombardo. Thank you so much.